yesterday with converting from degrees to radians and radians to degrees. Now, as we said yesterday, if we're going from radians to degrees, we want to find out what the degree measure is. We multiply the radian measure by 180 over pi. If we want to go to radians, we take the degree measure and multiply it by pi over 180. These are kind of the main two ways that we change from one to the other. And we did this for, I think, 135 in our negative pi over 2. Because I think the only one we didn't do was 2, yes? Now for 2 radians, we can multiply it, so we're going to degrees, so we're multiplying the 2 by 180 over pi. And unfortunately on this one here, we're not able to simplify the pi's out. They won't cancel out because our starting radian measure doesn't have pi in it. Because if we multiply this together, well, we do 2 times 180, which is 360 over pi. At which point we'll just approximate the final answer. Because we can take 360 divided by pi and get 114.59 degrees, approximately. Because we can't get the full result because, again, pi is a non-repeating, non-terminating decimal, so there's no way to get the full number. But that's as far as we go. Any questions on any of this here? We feel comfortable with converting from degrees to radians and radians to degrees? Yes. And probably at this point, I mean, over the last year or so, you probably noticed the 2 little graphics I have up on the wall between the calculators. This will start making a little more sense because, again, these calculators can be put in radians or degrees, one or the other. And so if we pull up the calculator, if you look at the top of the graphing calculator, it says radian. Y'all see that there? So what that means is the calculator for the graphing calculator is set to radians. So if you're using sine, cosine, or tangent, or any of the trig functions, it's assuming the angle that you're plugging in is in radians, not in degrees. The TI-30XS, these yellow calculators, are standard set for degrees. So the measure or this whatever we get out of these will be different depending on what it is, especially with sine, cosine, and tangent. Because as we look at this here, 2 radians is the equivalent of 114.59 degrees. That's a massively different number. Would y'all agree with that? So, depending on how the calculator is set when we plug it in and we start solving for different parts or different parts of the function, we'll change the answer. Which is kind of what both of those jokes are poking fun at. Kind of I think they've done many of these, are you sleeping kind of deal. The first one, hey, are you sleeping? Yes, what? The calculator was set on degrees, where everything was supposed to be in radians, or vice versa. Because again, this here, if we did sine, and we want to do 30 degrees, well, since it's in radians, it'll give us negative 0.98803 going on. To change it, all we need to do is hit mode, where it says radians. We can switch it over to degrees and hit enter. Yes, sir. Yeah. Second quit. Now I can do sine of 30, which is a half. So it gives us a completely different answer. Because for 30 degrees would be pi over 6 for us to get the same answer. So making sure that the calculator is in the correct mode when plugging these in, especially when we start dealing with sine, cosine, tangent, cosecant, secant, secant, cosecant, and cotangents, it's going to be helpful to have it in the correct form, or the calculator knowing the correct angle that we're plugging in. Questions on this here? Now, the next part we're looking at is degrees, minutes, seconds. For any of y'all that have dealt with a map, or they've shown maps for kind of locations in movies, especially action movies, the target is 32 degrees, 6 minutes, so many seconds longitude, and they do that latitude. Really, all the degree, minute, seconds, and they've kind of seen this, especially GPS, anything like that, it's taking a decimal version of a degree, an angle, and converting it over. So we're really looking at, so 110 degrees, 52 minutes, 11 seconds is really something like 304.98. We have a decimal going out, but instead of writing it as a decimal, they decided to write it as degree, as minutes and seconds. Well, interestingly enough, you know how many minutes they're going to be? Well, there's 52 here out of a total of what? 60. How many seconds do you think we'll have? 60. So, really, for each decimal, so there's 60 minutes and 60 seconds for each one of these here. And really, when we go from one to the other, from decimal form to degree, minute, seconds, or degree, minute, seconds to decimal form, we're dealing with 60s. So if I wanted to figure out this, 110 degrees, 52 minutes, 11 seconds as a decimal, taking it back into decimal form, what we would do is we would start off with 11 seconds and divide it by 60, because we're converting it from seconds to minutes. So we can say 11 alpha y equals enter over 60. .3 repeated. So what that tells us is that we have 110 degrees, 52.183 repeated. And we could do this here and then do the same thing this one here, because again, there's 60 minutes in a degree. So we can divide this by 60. Now the issue is trying to type in 52.18 and then 3 repeated, yes? Well, the nice thing is the calculator does have it here, yes? And all we're needing to do is add what to it? Add 52. So on the calculator, what we can do is say plus 52 and divide that by 60. So we get 0.86972 repeated. So that there would be the angle in degrees. Questions on what we did here? Does this kind of make sense how this works? Yes? 78 degrees, 10 minutes, 19 seconds. So again, we can do a similar thing. We can divide the 19 seconds by 60, add that to the 10, divide that by 60 again, and then add that to the 78. Or really what we're saying is, well, we're dividing the 10 by 60, yes? And we're dividing the 19 by 60 and 60 twice. Well, 60 times 60 is 3,600 is essentially what we're doing. And we're adding what those decimal numbers are back to 78. Questions on this so far? Now these calculators are pretty interesting, aren't they? With what they can do. Let's learn something new. 78. Because what is the angle we're talking about? 78 what? Degrees, yes? Right above the apps button, the one that says APPS, what does it say in blue? Angle, yes? So to really select anything that's in blue, we can hit second and select that there. Well, the first one's our degree marker, isn't it? So I can hit enter. So we have 78 degrees. Then how many minutes do we have? 10. So I can go 1, 0. Second angle, well, the one right below it is the same as our minute marker, isn't it? So we can hit enter. Was that it? Well, we had seconds, didn't we? How many seconds? 13, yes? 19. And if I look at second angle, I don't have seconds. I have degrees and minutes, yes? They're there, but I have to go to something called the catalog. So second 0, where it says catalog, this is pretty much the yellow pages of this calculator. Everything that it can possibly do is listed in the catalog. And it's in alphabetical order. So A through Z, and then numbers, and then symbols. But what we're looking for is a symbol, yes? So most likely, it's at the very bottom. So if we scroll up, it'll take us to the bottom since we started at the top of the list. And there's pi, and there it is right there. Questions on how we type this in? Questions on this here? Now we do need to go back the other way. We need to see somehow we can convert it back to degrees, minutes, seconds. Now, probably some of you already noticed when we went second angle, the fourth one down is DMS, degrees, minutes, seconds. So it'll convert it back. Which for here isn't anything real big because we already plugged it in at 78 degrees, 10 minutes, 19 seconds. But if we said 26.5 degrees, degrees, we could say we want to convert it to degrees, minutes, seconds. Angle 4. Yep. We didn't need the degree symbol, so I mean, this is one way we can do it. We can just plug it into the calculator if we didn't need the degree marker. Tell it degrees, minutes, seconds, and it'll write it out for us. And since the seconds is 0, we don't need to list it. So it'd be 26 degrees, 30 minutes. And that's it. Questions on this here? Now, I do want to show you at least one time how to do this by hand, if we were calculating this out. The way we would do this, if we were not plugging it straight into the calculator, is we would take the 0.98 and we divide the 98 by 60. Or sorry, not divide by 60, we're multiplying it by 60. So we're really saying plus, or not so much plus, because this 0.98 will be part of the minutes. So we're multiplying it by 60 and seeing what the result is. Now we can say 0.98 times 60, which gives us 58.8 minutes. So we have 304 degrees. And 58.8 minutes. Well, if we still have a decimal at minutes, we use it to get seconds. So any questions on this so far? So just like what we did to get the minutes, we're going to do almost the same thing to get the seconds. So we still have 304 degrees. Here we'll have 58 minutes. And to get seconds, we're going to take the 0.8 and multiply it by 60 to get our seconds. So really what we're trying to do is to get rid of the decimal. That's what we do with degrees, minutes, seconds. We're trying to get rid of that decimal. So we can say 0.8 times 60, bless you, and we get 48. So we'd have 304 degrees, 58 minutes, and 48 seconds would be our answer for this here. Questions on any of this here? Arc length. For a circle of radius r, a central angle theta intercepts an arc of length s given by s equals the radius times theta, where theta is the measure in radians. Note that if r is equal to 1, then s is equal to theta. And the radian measure theta equals the arc length. Now, we can find the arc length from this given equation, and we can calculate this out. Because again, to find the arc length s, we're really using this formula. S is equal to r times theta. Is the formula we're using, where theta is in radians. And looking at this formula, do we know what the value of r is? 4. Do we know what our angle is in radians? 240 would be the angle, but is it in radians? No. So unfortunately, we have to convert it from degrees to radians. And to convert from degrees to radians, we're taking 240 and multiplying this by pi over 180. And again, at this point here, we can plug this into the calculator to see what we get. But we know for certain that our answer is going to have pi in the answer. So we're really looking at 240 over 180. So 240 alpha y equals enter over 180, which is 4/3. So that tells us that the angle is 4 pi over 3. Questions on this here? And that makes sense, especially if we look at the figure, because straight up is pi over 2. Straight across would be pi, and straight down is 3 pi over 2. So 4/3 is bigger than pi, straight line, but it's not so much that it's bigger than 1.5. So it makes sense. If we think about the angles and what we get, that's kind of the angle we would expect to find. So what we can do is plug in 4 pi over 3 for this here. And last but not least, we just need to multiply. Now, the exact answer, we do 4 times 4, which is 16 pi over 3. Would be the exact answer. And if it asks us to approximate or round, then we need to approximate or round to a certain number. And the approximate answer is 16.755 if we're going out 3 decimal places. But again, when we're approximating at this point, it's really just plugging it into the calculator and seeing what we get. Questions on this here? Linear speed and angular speed. I have a feeling that you all have at least heard of both of these terms. Yes? Or now, linear speed is considered a particle moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in time t, then the linear speed v of the particle moving is described by this here. Linear. What does linear talk about? It's a line, yes? Can y'all think of when this would be nice to know the linear speed of a circular object? Well, hopefully we knew that trying to get here. Tires. Because again, what we're talking about is a circular object moving in this kind of direction. How is it moving based off the arc's travel? So we can use that to calculate, say, the speed of a car, how fast the tires are moving, so we know how fast the car is going. Now, moreover, theta in radians corresponds to the arc length, s. Then the angular speed, the lower Greek letter omega of the particle is this here. So we're talking about angular momentum. How much is it changing in the angle? So we're talking about this here as it's spinning circularly. How fast is that angle changing? And we normally talk about this angular speed as kind of revolutions per minute or per second. This one's not as common or well known or kind of thought of, especially if you've seen kind of little toys where you pull it and it kind of displays a message. That is talking about the angular momentum, how fast it's spinning. More of a linear, more as a rotation. And then we can also find out areas of a sector using this. And we've done this before because we did area of a sector in geometry, but we didn't see it in this form because the main way we saw it was arc degree over 360 times pi r squared is how we looked at it. But we also know that 360 is the same as 2 pi, yes? Because we're talking about radians. A full circle in radians is 2 pi. Bless you. Well, if I multiply this and this here, what happens to the pi and pi? They cancel each other out. So all I'm really left with is our arc degree, which in this case, so arc in radians, which we can just call theta over 2 times r squared. And if I want to put the theta out here with r, that leaves what on top? It's the same formula, just simplified a little bit. Questions on this here? Well, that's the end of chapter 1, or section 1.1. Not chapter 1, that'd be a little fast. So 11 and 12. Determine the quadrant in which each angle lies. So these are both in radians. So I would use the graph I gave you and try to get them back to positive, because if they're negative angles, we can add 2 pi to them or add 2 to the fraction to get it back between 0 and 2 pi. 15 through 18. 15 and 16, determine 2 coterminal angles, one positive and one negative for each angle. Give your answer in radians. 17 and 18, find, if possible, the complement and supplement of each angle. So if it's not possible, we just say it's not possible to find one or the other. Most likely, you're not going to find a complement. Supplement is more likely to be able to find on all of them, but complement is less likely, especially if the angle is over pi over 2 or 90. 25 through 32, so 25 and 26, determine which quadrant each angle lies. 27, 28. Overzealous, sorry. Do not do 27 or 28. I'll have to fix that. Because 27 and 28 is sketch each angle in standard position. I don't want you to sketch it. 29 and 30, determine 2 coterminal angles, one positive, one negative. 31 and 32, find the complement and supplement. 35 through 38, convert each angle from radian measures as a multiple pi, so you're going from degrees to radians for 35, 36. 37, 38, you're going from radians to degrees. And then 47 through 50. 47, 48, convert each angle to decimal. So you're going from degrees, minutes, seconds to decimal form. And 49 and 50, you're going from decimal form to degrees, minutes, seconds. And that's it. So don't do 27, 28, but you will do the rest of those.